Okay. So good afternoon. My name is Fabian. So my talk might be a little different from the ones that you've seen so far. So I currently live in matrix land. Okay, so everything is finite dimensional matrix algebras, and we'll try to use these tools and these means to understand coupled cluster theory a little better. So let's call this CC theory. Yeah, maybe an algebraic perspective. Okay. So you have already seen the CC ansatz. Yeah. So the idea is that our wave function is expressed as e to the t applied to phi 0. Okay, and I might switch notations. I might go from mathematics to Dirac notation. So please excuse this. It's just a habit. So in this ansatz, our wave function is written as the exponential of a matrix applied to some a priori picked vector phi 0. So this can be really any Slater determinant that you can think of, but most commonly we choose the Hartree-Fock solution here. So with this ansatz, when you plug this into the electronic Schrödinger equation, I'm already switching. So you see we find e to the t phi 0 is equal to e t phi 0. And then since the exponential of a matrix is always invertible, we can move this over and we find and then you see, well, now if we project onto the reference phi 0, we recover the energy. And now I'm switching. And if you project onto anything that's orthogonal to phi 0, you'll get 0, right? So usually we do the standard Galerkin trick, and we form a basis of the orthogonal space and project onto this one. This is known as the coupled cluster energy, and these are the coupled cluster energies equations, right? So what we have not seen in detail is how we are actually going to attack to solve these equations, right? Because one argument for why we cannot directly diagonalize H is its size. And now here we are suggesting to find a matrix T that's of the same size as H, right? Otherwise this product is ill-defined. And we, on top of that, want to take the exponential of this matrix. Yeah. Now, how does this make sense? In coupled cluster theory, there's a number of stroke of lucks that come into play that actually make this theory work and so powerful. And the first one is that this BCH expansion, or this similarity transformed Hamiltonian, actually truncates after exactly 5 terms. Okay. So in general, e to the minus th e to the t is a sequence of nested commutators, right? That in principle has to be expanded all the way to infinity. But in coupled cluster theory, we actually stop after 4 terms. You'll find H plus HT plus HT. Continue here. Okay. I missed a T. I did, yes. Thank you. Okay. So we get this expansion. So it's actually really just 4 terms. So now let's try to look into a bit closer what these terms mean. So the first one is clear. The second, that is right. So I did not prepare the proof. I was hoping Hassan did that. I think that's generally the assumption, right? The other person does. But this can be actually proven rigorously. Yeah, so this works for those who know couple cluster theory for any level of truncation. Now this works in general. Couple cluster equations always have this structure. Yeah. So let's look at the individual terms. The commutator you all know. The double commutator is already a bit funny. Yeah, so if you work this out, you find ht squared minus 2 pht plus p square h. Yeah, so it's quadratic. Yeah, the triplet commutator is already getting longer, and then the last one is yeah, they get h t to the 4 minus 4 th t3 plus 6 squared minus 4 t. All right. So this is how these commutators look like. Okay, and then for each of the terms, we have to then take the projection. So apply the reference from the right and project onto a corresponding basis vector from the left. Now, one thing that stands out in this equation is that it's of fourth order. Okay, so the couple cluster equations are a set of polynomial equations of degree 4. Yeah, so this is why an algebraic perspective actually makes sense. Yeah, so we have a very high dimensional system of polynomial equations that we are trying to solve. So what do we do? So the question is, how do we solve a system of polynomial equations? Yeah, so we want to find roots. And conventionally, what we do, or what anyone would do in the first try, we would apply Newton's method, right? So and this is really what most quantum chemistry codes are doing. So they apply Newton's method. They assume they are reasonably close to the targeted wave function, and then apply Newton method as you know it. Yeah, well. Something like that. So what is the general problem with Newton's method? I'm asking into the round. Let's make this a bit interactive. Exactly. It converges to the closest solution. And so I had a problem. this converges to the closest solution. Now, if you're close to begin with, you're fine, right? But if you're not close to begin with, or the closest root is a non-physical one, then you're in trouble. Yeah, and this, again, this is a high-dimensional system of polynomial equations. It's hard to say how many roots are there. And actually getting good estimates on the number of roots is still ongoing research. So I would like to illustrate why Newton's method can have severe problems. So let's look at the simple polynomial, 1D, fz is cube minus 1. Okay? So we're looking for roots of unity here. We know where they are. So we make a plot of the complex plane. We know one solution sits on 1. Then the other solutions are a complex pair somewhere here and here. Okay? So then if we were to go ahead and do our calculations and start Newton's method from any point in this, in a reasonably large box, and we were to color to which solution we converge, we get what's called the Newton fractal. Which means that, so we know if we start somewhere close, we should be fine to converge to this solution. Yeah? And vice versa, if we start somewhere here, we should also be fine to converge to this solution, and same holds for this one. But now something funny happens. So there are certain branches that go along this axis and these axes, along which you see a self-repeating pattern. Okay, so I'm trying to sketch it. Okay, and along these axes, you see very interesting things appearing. So within the big blobs, your Newton's method shoots you through the origin towards the other solution, although this is arguably further away than this one, or clearly further away. Same happens along this axis and this axis. So this is called a fractal because once you start zooming in, you see this repeating pattern occurring along all these nodes. Yeah, and if you were to zoom in here, you see again, there are the branches fiddling out from within, you converge to different points. Yeah, so there are regions in here which take you to the green solution, and then there are some that take you to the blue solution, and then there are some that take you to the red solution. Yeah. I have a very nice picture that I can share with the first 2 lines. Yeah, 2 rows. Okay, so I was hoping we could do this like a semi-digital, but I think it's too much hassle to bring this down just for 3 slides or 3 pictures. Yeah. So the catch with these fractals is you're fine if you start locally around the solution that you want to get. But what happens if you start, let's say, around 0 or any of these nodes, right? Then you're bound to, if you have a very small disturbance in your initial state, you might get from one point to here, or to here. And so global convergence of Newton's method is very complicated, and I don't know to what extent this is fully understood. Okay. So the question becomes, well, what does that mean for CC theory, right? As a chemist, you might just wave your hand and say, well, we're always close enough. But that's not entirely true, I would argue. Okay. So let's try to answer this question. So this is all just part of the motivation for why we should look into algebra, by the way. Okay, so we haven't started with. So what does this mean for coupled cluster theory? Yeah. If we want to use Newton's method, or for the sake of matter, we have to ensure that we are close to the sought solution. Yeah. But the big question is how? How can we do this? And I would say this is not always the case. Now, it's not always that easy. So one example could be we take a version of H4. Okay, take 4 hydrogen atoms and put them on a square. Okay, so like a 90-degree angle here, and some bond length here. So for this system, we can actually converge coupled cluster theory. Yeah, so it's, of course, it is degenerate due to the symmetries, but you can look at the performance of Newton's method, and this is the exercise here. Right, so we want to see what happens if we slightly start perturbing the solution. Can we learn something about the basin of attraction of coupled cluster theory? Because you see, already for one single polynomial, drawing Newton's fractal is a 2D endeavor. So what if we have something that lives in extremely high dimension and is a 4th order? It's much more complicated. So we just try to learn something. Okay, so what do? We find one CC solution. Yeah, let's call this T0. And it fulfills our coupled cluster equations. So FCC T0 is equal to 0. And then we start to perturb. Yeah, and we randomly perturb, but we try to make sure that we don't perturb too much. So we perturb with relative to the size T0. Okay, so let me try to write this down. So we initialize T init is of the form T0 plus some parameter alpha. And then we have the norm of T0 times TP. Okay, where TP are random CC amplitudes, and TP is of norm 1. Okay, so this exercise is, we start from these solutions. We know here CC equations are fulfilled. Newton method obviously converges after one step because that is the solution. But so what happens if we slightly perturb this and look in a region around T0? How will our convergence look like? Well, you do this and you run, let's say, 1,000 iterations, and you look at the success rate as a function of alpha. So here we have success rate 1. Here we have alpha equal 1. And we can pick some larger value of interest. In our case, 1.25. Yeah, and you do this. And then you see it works well locally as expected, but then it drops down. Yeah. And it flattens something like this. Okay. Now the point alpha equal 1 is interesting because you can think of it this way. Yeah. Let's plot the size of T0. So let's say T0 is somewhere here in our, this is a 2D representation of the cluster amplitudes. So we have one region that's up here where we get pretty high success rate. Yeah? So this is some value. And the case that we've done, it's a slightly under 0.25. So let's say it's around 0.2. You know? So that means that for the couple cluster amplitudes to nicely converge in Newton's method, you can draw a ball around your thought solution that is of size 20% of the cluster amplitudes. It's relatively small. But within this region, you get a success rate of larger than 97%. So what happens if you go past this? It gets lower as expected. And 1 is interesting because this is exactly the size of T0. So if you really draw a ball around T0 that goes through the origin, then your success rate is extremely low. So in particular, starting from 0, based on this interpretation or based on this experiment, should not give you what you want. But most of the time it does, right? Because you start Hartree-Fock and initializing quasi-Newton from 0 gives you in the first iteration MP2. And starting from MP2 is reasonably well. So for most cases, this works. But for this simple 4-hydrogen system, we observe that if you are completely oblivious of the meaning of MP2, drawing a ball of the size of T, which corresponds to starting in 0, has an extremely low success rate. So let me give you the number. Oops. Yeah, so this is around, if you go up here, it's around 27%. Yeah. So what this little toy problem tells us really is that the Bayesian of attraction of couple cluster theory is highly non-trivial. Yeah? And really assuming that MP2 or 0 is sufficiently close is obviously not true. So there's other physics that comes into play and that have to be taken into account. And thinking that this applies to any physical system or any chemical compound that we have in mind seems rather naive from the perspective of mathematics. Yeah.
So what is your reference wave function here? Because you have two degenerate orbitals and you have 4 other points, so you have, it's not just
that's right. Yeah. So all these things come into play. So we picked one of the two. Yeah.
Closed shell one?
Closed shell. Yes, this was closed shell calculations. Yeah.
What explains the volume? It's not totally flat for a small region when alpha is very small. Why explains it for you?
So it's a bad. Okay, so I can maybe share again the plot with the first row. So in the very beginning, it is perfectly flat, and then it drops down. Okay. Yeah. It's my bad drawing. It's like a perfectly flat, and then it comes down. Yeah. There was another question. Yeah. Yeah.
But it's, I mean,
Yeah.
So where
Right.
it's not just
Right. But you could argue, I mean, it's 4 electrons, right? In minimal basis, you have 8 spin orbitals, so that's, you can still fully diagonalize that. So yeah.
really bad for the starting point. This is just to say that it's not
Yeah. No, I wanted to use this as a motivation that we have to go kind of beyond this, right? So we don't want to, there's a fair point in trying to hammer on Newton's method and try to make this better, converge faster, more robust. But an alternative line of research is in fact to study the polynomial system as is and try to solve that. And this is what I'm trying to motivate.
For the system, you have the QCI solution, so.
Yeah, for this system we have. Yeah.
So you can check everything.
Exactly. This is why these small systems are extremely useful for us. Yeah. And this sort of touches upon the point. Yeah. So maybe we should try to compute all CC solutions. Yeah. So in general, this goes now a bit further. How do we compute all solutions of a polynomial system? Any ideas? There's really one, as far as I know, only one dominating method that works. And this is, these are homotopy methods. Okay. So homotopy methods work in a very specific way. So let me just sketch the idea before we start with the with a bit more formal math. So the idea of homotopy methods. So we have a target system that we want to solve. Yeah. So we have target system. In our case, these are the CC equations, which we want to solve. And we have given, or let's rather say this is want. Yeah, and we have. We have a start system. And we call this often G. So G has to fulfill certain properties. Yeah? Most importantly, G has to have at least as many solutions as our target system, ideally slightly more. And then what we do is we transform G into F. So the easiest way you can think about this, we introduce a parameter lambda. So we call this lambda G. So this goes from lambda equal 1, transforms from G as we go to 0 to FCC. So this is the usual convention for homotopy methods. You let lambda transform from 1 to 0, not from 0 to 1. The reason is that there are certain numerical techniques. Once you get closer to the target system, your solution paths might behave awkwardly, and you can control this better if lambda is small rather than a small deviation from 1. Yeah. So you define the system. Let's call this H lambda X, G X. And we know in 1, this is equal to G. We know the root structure of G. And then we slowly increase lambda and, in quotation mark, follow the roots. So there's a governing equation that does that. I'll not write it down today. Maybe we'll get to this tomorrow. But what you end up with is the following picture. Here's lambda. Here's 1. Here's 0. And 1D representation, again, so we have roots that sit here, 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 for example. Yeah. And we have our final system. And let's say this has 2 roots, you know, for sake of argument. Okay. So then what you can see is that these curves behave kind of funnily, going around here. These are the roots of H as you transition lambda from 1 to 0. So it might be that they can cross, that's allowed. They can even give the same root, this is also allowed. And most inconveniently, diverging solutions are also allowed. So if you pick too many, you might end up with your solution boosting up. And then the question becomes, does this solution just get to a very, very large value, or does it actually go to infinity? And this is where so-called endgames come into play. And this is why we transition lambda from 1 to 0, because you really have to fine grain this area. Whereas if you try to fine grain around 1, at some point your mantissa is full and you don't resolve the area that. All right. Yeah. That's right, yeah. I mean, this is a homotopy H. Yeah. So usually the restrictions on G are not that harsh. So I only use this numerically, right? So I don't do the math, but
In what? In lambda?
Yeah.
The continuity in lambda is, you mean the continuity in lambda and what variable? Because lambda is there, I don't.
So in your case, F and G are polynomials.
They're polynomials, yeah. So these 2 are polynomials, yeah. So they should be fine. And then lambda, yeah. So I never encountered this question. Maybe it's not there, I don't know, but I never had to scratch my head, you know. Yes?
What are the solutions diverging in 1, leading to solution in 0?
Sorry?
What are the no solution diverging in 1, and then bring the solution symmetric to this one?
So I don't understand the question. Diverging?
So starting from 0 is diverging.
Yeah. And then go up?
Yeah.
Oh no, well, I mean, this is where you start with, right? So I mean, if you have a solution coming from above, then you have underdetermined your system to begin with. So this can only happen if your start system has fewer solutions than the other one. Otherwise, they will either collapse or diverge. But it's not possible that you miss a root if you have enough to begin with. Yeah. Well, it could, but again, you need more in your target system.
You may miss what you say, that you don't miss solutions.
But you have a number of roots you start with, and then you along this path, right? You keep this number of roots, and you keep deforming. So the only way that another solution comes down and gives you one here, I mean, how to say? The number of roots is conserved, yeah, unless your final system has fewer roots. If you have exactly the same amount, the roots are preserved. Exactly. We just look at this function. I mean, you try to enforce 0 for every value lambda, and you make a small increment, and your roots, I mean, they might move aggressively, but I don't know how to say it.
You need some assumption somewhere.
Yeah. Oh, so if your target polynomial is 0, then all of the roots should collapse. Because I think they should collapse. Yeah.
Is it point
Yeah. Let me. Yeah. Maybe they.
Singularity between.
Yeah.
To lambda 0 and 1, if there is a singularity, one.
Yeah.
Just it can come from down.
What?
If there is a singularity.
Yeah. Here?
Between 0 and 1.
Yeah.
I told you.
Okay. Yeah. Yeah.
It can appear mathematically.
Okay. Well, let's put a pin on that. Okay. I'm not the homotopy expert. I'm just trying to advertise the use of that in couple cluster theory.
So typically, the G system would be a simplified version of the couple cluster.
That's right. So typically how we use this, right? We try to get an estimate on F, how many roots F has. And then we build an initial system that has as many roots as our guess is, right? And then for each of these guesses, we track the paths. And what we actually see numerically is we never get any crazy situations like this. Yeah, it's rather that our guesses for the roots are too crude. So we heavily overestimate the number of roots. So we waste a lot of numerical resources to actually get all the couple cluster solutions. Yeah, but we find all of them. So they always collapse. We never see any strange things like this happen. We often have diverging roots, but these you can drop anyways. Yeah.
You find all of them if G has more solution than F.
Yeah. Yeah.
That's not completely straightforward to find. A level of theory that has more roots than the actual double cluster.
So I don't think. Okay, so let's discuss this as we get there. But I think you can actually claim that you have more solutions than FCC. You can guarantee this, and you can guarantee this pretty close to the number of generic roots for CC. Yeah. Complex. Yes, because the complex theory for polynomials is just much more accessible. Yeah.
But your CC includes applications,
Mm.
are they real?
So that depends on the code. I mean, a lot of code has real, but you can also have complex couple cluster solutions. And I mean, yeah, we just compute all over the complex field. Yeah. There was another question. I see. Yeah. Yeah. Okay. So this is great. Lots of questions and discussions. So in order to develop this theory and come to the results, I need something that's called second quantization. Okay, so we will talk about this for a bit. But this is nice because it's a nice matrix theory. Okay, so fermionic Fock space. So the starting point is very similar to what you have seen so far. We pick a set of functions, let's call them phi. And again, I live in matrix land, so I have only finitely many. They are sufficiently smooth so that I can take all the derivatives necessary in the Hamiltonian. And then I form the m-particle Hilbert spaces. So the m-particle Hilbert space, HM, consists of m-fold m-fold exterior products of these functions phi I. Okay, so how do I do this? Yeah, it looks something like this. So I take my functions phi, I have k of those at hand, and I take an m-fold exterior product, which are these later determinants. At this point, I don't even enforce that they are amongst themselves ordered in any ways, but these functions span my m particle Hilbert space. Make sense? Okay, so the Fock space, call it F, is the direct sum of my m particle Hilbert spaces. Okay. So let's look at an example. So I will now introduce Dirac notation of an occupation vector. So I look at what orbitals of my k-many that I have at hand are actually used in my exterior product. So I have indices S1 through Sm. And fair enough, for the sake of a Slater determinant, I divide by R1 over m factorial. I'll redefine m in a second. And you have phi1, S1, wedge, all the way to S phi. We had k-many, Sk, sorry, this is k. Yeah, and the constant m. Okay. Yeah, so these are the Slater determinants that I could form. And then a general element in my Fock space looks like psi is equal to the sum of 1 okay. All right. So far, so good. So before I want to transition into the tensor product and the matrix representation, I want to introduce one more concept. Then these are creation and annihilation operators. Okay, so we have how these later determinants look like, how a general object in the Fock space look like, and then we can define AP dagger as a function that goes from the Fock space into the Fock space. And it works on these later determinants. -1, sigma p, 1 minus SP, and then we have S1, who, well, SP -1, and we have 1 minus SP. Okay. Let's see, is that right here? See, I think here's a typo. Let's see. And sigma p, so sigma p is a phase. Okay, so what's going on here? The dagger, right? This is supposed to create a particle. So we have our Fock state, and we want to generate a particle at site P. So we first check how many S's before the Pth entry are actually 1. And this is captured by the sigma P. For every particle that sits before the site P, we pick up a negative sign. That's why you have -1 to the power sigma P to the power sigma of P. So then if SP is 0, we populate the site. So we get 1. If SP is 1, 1 minus 1 gives 0. And but we want to make sure that we do not populate every site more than once. So we have to map this to 0, and this is what this factor in front does, right? So if SP is 1, this factor throws whatever we have onto 0. All right, let's look at AP. So AP is supposed to kill a particle that sits on site P. Again, we pick up a phase for every particle that sits before the site P. And then if we're here, if SP is 1, we get 0. But if SP is empty, we also want to avoid to kill a particle where there is no particle sitting. So this is why we have the factor of SP in front. All right. So this is a definition of creation and annihilation operators using the wedge product. But computationally, there's a much easier point of access to this whole thing. And these are tensor product spaces. So it's important to note that any Slater determinant can be expressed as such an occupation vector. So each entry is either 0 or 1. So you just take a tensor product of 2-dimensional spaces, like a k-fold one. Okay? This is the and this brings us into matrix land, finally. So we have tensor product representation and ladder operators. So note every Slater determinant is uniquely determined by a binary string. So this implies that our Fock space can actually be written as, if we choose complex amplitudes, C to the 2k. It's a binary string of length k. So it looks like this. And then we introduce the following conventions, right? So these are conventions. Yeah. Okay.
If you favor determinants and what orbital, would you say that the determinant is the same or it's a different one?
Well, it has a different sign because it's an alternating product.
Yes.
So if you swap two,
Yeah, you change
Yeah.
the sign.
Yeah.
But then because so for them to be determined by binary string and a sign or
so in the binary string, you don't see the order.
There is no anti-symmetry in terms of computation.
It's every Slater determinant made of functions in the basis for the Y.
Yeah. So you still span the space but I agree in the binary string you don't see the sign. Yeah. Yeah. That's true. Yeah. In terms of expressibility, the sign doesn't matter, right? But it's true that in this formulation you clearly see, if you take the wedge product, you will clearly see the sign, whereas here you don't. Yeah.
You have to define them like that, no?
Yeah. Yeah. So usually when, okay, so I say we, but when I work in first quantization, because I want to have a basis of slated determinants, you always assume that these indices are increasingly ordered, and then you don't have this situation, because then swapping, I mean, there's a unique representation of the slated determinant. But yeah, in principle, if you define it through the span, you have this overdetermined situation. Yeah. Yeah. But I like the idea of fixing in order. That's yeah. All right, so here's the convention. So we define 1, 0 to be unoccupied. And we define 0, 1 to be occupied. So this is just a convention, and you can pick your own, but usually people impose this. So then we can write any slated determinant in this form. Okay, so depending on whether or not you're on or off, you'll get occupied or unoccupied here in this tensor product. Yeah. So let's look at an example. We look at the state 0, 1. So 1, 0. Tensor 0, 1. Something like this. Okay. Now, in this perspective, the creation and annihilation operators take a very convenient form, right? Because really what we want to do when we apply AP to the P site, we want to either flip from unoccupied to occupied, or from occupied to unoccupied. So A, which annihilates a particle, should map occupied to unoccupied. So it's like, looks like this, yeah.
That's
So what?
I'm missing a 1? No, this is fine. This is the tensor product. Right? So you multiply this number by this vector and this number by this vector. Yeah?
stupid question, but why using a 2 integers instead of only 1? Like, let's say, not occupied 0, occupied 1.
Where now?
So
By using the tensor product instead of what using the right hand side instead of the left hand side.
So yeah, if I had to reduce my
Yeah.
storage in terms of
Yeah.
memory, I would code unoccupied by 0,
Right, right.
occupied by 1.
Right. So my explanation, yeah, and correct me if I'm wrong here. This, although it's nice to write down mathematically, this is not easy to parse for me, right? Whereas if we switch to the tensor product formulation, we get actually very nice matrices, and I will, if I still have the time, we'll get to the point where the sparsity of these matrices can be leveraged to do some computations really fast. Yeah. So yeah, let's see where this goes, and then yeah.
Very active.
Yeah, a dagger looks correspondingly like this. So let's try to build up the creation and annihilation operators that work on the corresponding sites. Yeah, because now we just have it work on one state vector, but we have the tensor product. So the one thing that is missing at this point is to pick up the signs for those electrons, for those orbitals that are occupied before the pth one. Okay. How would we, anyone, any idea on how we can generate the phase? So we are looking for a matrix, right? When we multiply it to unoccupied, gives 1. And when we multiply it to occupied, gives -1. Yes, I know that you. Okay, this is the Pauli Z matrix. Yeah. Pauli Z matrix, 1, 0, 0, -1. So if we apply this to any state vector, we get 1 if it's unoccupied and -1 if it's occupied. Right? So this means that our general operator, AP dagger, looks something like Pauli Z, tensor, Pauli Z, tensor AP. Here we have P minus 1 many. To the identity, okay? And we can just put this in brackets. Okay? Any questions on this construction? No? No. All right.
So here you don't have the AP, right, in the middle. So
Yes, I just have the A, of course. Sorry. Yeah, because I defined A and A dagger, and then we define AP with A and A dagger. Okay. Okay, so then you can formulate, well, first observation. Yeah. So the fermionic creation and annihilation operators fulfill the canonical anti-commutation relations. Yeah? So they fulfill canonical so they form a car algebra. So we can actually prove this. Oops. So the proof is built upon the property that if you have a product of two tensor products, the individual matrices get multiplied with each other. And Pauli Z matrix is a self-inverse. So Pauli Z times Pauli Z gives identity. And then the only thing that you have to note is if you have the situation, maybe we write this out for one term. Yeah. So we look at AP times AQ. And let's assume that P be smaller than Q without loss of generality. So we can write AP AQ as identity all the way up to the pth site. Okay, and in the pth site, we have A poly Z and then you know that this here is equal to minus A. Whereas if you have poly Z times A, this gives you A. Yeah. And then you can show, well, this is equal to minus AQ AP. So this is sketch, right? And then you can show the other. Cannot do who does not know how this works? Okay, fair enough. Let's do this. Okay. Okay. So let's pull out the minus sign. So this gives us minus identity times the identity. And now I'm trying to be pedagogical. We write times A times poly Z times A times identity.
This mistake sigma Z A result, it's just
This one doesn't have one. So
when you make A sigma Z, and then it should be sigma Z A, right? Same operation.
Yeah, you can, but we are saying that it's minus 8, also minus 8, minus.
I see. Sigma Z A, it's just one position, it's a Q position.
so I have A, right?
No, but you make sigma Z A, it's one position, so it's this operation. You don't have the product.
Yeah, I know, but we say the also is why, sigma.
In here?
No, the other one.
No, this one.
Okay, well, go ahead.
So I think this is fine.
Yes,
fine.
this is right.
Okay. Okay, let's see where this is going. So what I want to do is I want to pull out the minus sign. And now I want to sneak in. I want to sneak in a sigma Z, because if you look at it, you apply sigma Z from the left to A. Then you get A, right? So without any harm, I can sneak in the poly Z here. Okay, and then I see that what I've just written down here, this term is equal to AQAP. Yeah. Yeah, and we have assumed without loss of generality that P is smaller than Q, but the case where P is equal to Q, well, you get just a bunch of identities, and then you have A square, which is again the identity. No, let's see. Which gives 0. Sorry. Yeah, for those who, is that more clear now? Yeah. So similarly, you can show that AP dagger, AQ dagger, also anti-commute. No? So what you will find is that AP, AQ equals 0. So these are the anti-commutation relations. And they can all be proven in the similar fashion as this one. You multiply the individual tensor products and you identify identify these terms with each other. Okay. And now I get to the point for why these matrices are extremely useful, right? So these matrices have these properties. And ultimately, what we want to evaluate are matrix elements. Remember, at the very beginning, we had that the CC equations consist of terms like H times T. This was one part that popped up. So if you write your Hamiltonian in second quantization, you know that H it looks something like this. And what we will see in a second is that T can as well be expressed as these creation and annihilation operators. So we'll have terms appearing, okay? Or let's put it this way. When we want to evaluate the CC equations, we will end up with terms that look something like phi mu, AP dagger, AQ, and then we have certain terms coming from T. AR dagger AS applied to phi 0. Okay, so we have to find a way, if we want to do computations of any sort, to evaluate such integrals rather quickly. Okay, and what we do not want to do is we don't want to build these exponentially large matrices because they're huge but extremely sparse. So we don't want to build them and do these products and then take the product of this large matrix with this vector and then take this vector product here from the left. But what we rather want to do is we want to use so-called contraction theorems. Okay, and these are the big benefit computationally that second quantization has. Okay, so let me elaborate. So let's take the following example. Let's assume our Hamiltonian, just for 1 second, consists only of single body terms. And let's assume we have a 2-electron wave function, right? So we want to evaluate the matrix element of this matrix that corresponds to applying a two electron Slater determinant from the right and a 2-electron determinant from the left. Yeah.
Why the indices in the random interaction from this point and Q is not the linear?
Right. So this is a good question. So I use chemist notation for this. So when I write down VPQRS, it looks like this. So I have a double integral phi p dagger R1 phi q R2, and then phi r R2 and phi s R1. Oops. Okay, so in this notation, there's no spin. Usually, if there are spin orbitals, these guys would also have a spin variable. But the catch is that these VPQRS are defined with the complex conjugate sitting on P and R. And then I have to account for this in my creation and annihilation operators. So this is chemistry notation. And the physicist notation would rather be like a Galerkin projection. So then the indices would be swapped. But the one thing that is important is that the computation of the two particle integrals, so the ERI, is consistent with the order of these creation and annihilation operators. Okay. Okay. So back to this. So let's assume we want to look at AP dagger AQ. And let's say we are interested in the matrix element that corresponds to applying the 2 electrons like the determinant from the right. So that will look like A dagger R, AS dagger applied to the vacuum. And from the left, we have I and J. So this would be a single Slater determinant if 2 particles occupying R and S. And this is a Slater determinant, 2 particles occupying I and J. Okay. So then we can use linearity, and you'll see that all of this boils down to a very fast evaluation of terms that look like this. Okay. So now what have we gained? Well, we got the vacuum. That's something. But then we have more matrices in the middle. So I just replaced the problem by really imposing more large matrix products in the middle. But there's an important observation, and that is if we have a creation operator acting on the vacuum from the left, it is 0. Okay. So note PQRS running out of variables. This is equal to 0. Okay. And now you see the game arises. Okay. So what's the game? We want to move the daggers to the left. And the rules of the game are we can swap according to these rules. Okay. So I'm not going to do all of them. I'm going to do a few, and then I'll show you how to do this quickly. Okay. So let's do a few slow ones. Okay. So now we know there's a sum. We'll only look at this term here. Okay. And let's say we want to swap P and J. So P and J corresponds to this scenario. So we can swap at the cost of a sign. So let's write down this term. So we get AI, AP dagger, AJ, AQ, AR, AS at the cost of a sign. And if it happens that P and J are the same, we get a Kronecker delta. So plus PJ vacuum AI AQ dagger dagger. Fair enough. Okay, and then you see, well, we moved this one closer to the vacuum state, and we obtained a delta, but shrunk the string of matrices by 2. Okay, so then we proceed. So we do the same thing one more time. I'm not going to write it down now, but you can imagine you swap these two. You can swap at the cost of a minus sign, but we don't care about this part because P dagger acts on the vacuum, that term gives 0. So you end up with a delta IP acting on this string of that length, and we can also start pushing the daggers through on this end. So this is a very lengthy calculation. Takes you maybe half a page or so. And you do this. And at the end, what you'll find is that this expression is really just a product of Kronecker deltas. So you'll find delta Pj. So I write this down because I'll show you how to do this quickly in just a second. Delta IL, delta Qk, minus delta Pj, delta QL, delta Ik, minus Pi, Lj, Qk, plus delta Pi, QL, delta J. Okay, so this actually reduces to 4 summons of delta products. Okay, so the evaluation of this one is super fast, right? This takes no time. Whereas if we do go the naive round, we have these gigantic matrices, we multiply them. This is very, very costly.
R and S, and then your L.
Whoops. Ay, ay, ay. So these are now L and K. I should stick to my, yeah, I don't like looking just all the way on the tablet. But yeah, L and K, you're right. L and K. Now it should be consistent. Yeah. But the cool thing is, you can do this really, really fast, okay? And this is what I want to show, because this is a really useful theory. So this is called Wick's theorem. So let me copy this part with the indices correctly. So we get AI, AJ, AP dagger, AQ, and then AL dagger, AK dagger. Okay, so Wick's theorem tells you that integrals of this form, or actually any string of creation and annihilation operators, only has a very few number of terms that contribute non-trivially. Okay, and these ones you get with so-called you form complete contractions. And what is a contraction? For example, so I write down this term, AI, AJ, AP dagger, AQ, AL dagger, AK. A contraction means I draw a bracket on top of a pair of creation and annihilation operators. Okay, so it always has to be a creation and an annihilation operator that I connect with such a bracket. And I'm only allowed to connect creation operators that stand to the right of an annihilation operator. Okay, these are the rules of the new game. Okay, so how many contractions can I form in this way, looking at this string? You can do 4, exactly. Hmm? Yeah, so let's write down the 4. 4 is the correct answer. Huh? So can you do one like this? And then I'll do another one. So another one would be, I go from here to here, for example, from here to here, or from here to here, right? And we do another one. Let me see. I get the right ones. I can take this one to the 11th one. I can connect these ones, and I can connect these ones. And AI, AJ, AP, AQ, AL, AK. So which one is missing? I guess this one. Huh? Okay. So these are all the contractions that I can take. Yeah. So daggers to the right, non-daggers to the left, and they can only connect pairwise. Now the crux of Wick's theorem is that those indices that are connected give me a delta. So this one will correspond to delta J P, delta QL, and delta IK. And the sign is determined by the number of crossings of these brackets. So here I have 0 crossings. So -1 to the 0 is 1. Do the same here. We get a delta JK, delta IP, JI, and QL. I see I have 1 crossing. So -1 to the 1, minus 1. Okay. And so I continue. Delta JP, delta IL, and delta QK. Again, there's 1 crossing, minus. And here at the bottom, I get delta IP, delta JL, and delta QK. Minus, minus, plus. Okay. And these are the 4 contractions. Let's see. Now I hope I didn't swap the indices around too much. But if you, maybe I did I? Okay, well, the signs come through swapping indices. So the thing is, if you compare this with the very lengthy calculation that you do here by swapping only two terms and picking up minus sign, you actually see that Wick's theorem gives you the right result, okay? And this touches on actually very interesting mathematics, right? Because you're looking at how many transpositions can you have of your string under the constraint that daggers are to the right and non-daggers are to the left. And then how many of those correspond to crossings? That gives you the sign, okay? So Wick's theorem is practically interesting, and I would argue also mathematically interesting, although I haven't worked it out yet. Yeah.
Is there a version in adapter with the E generator?
Spin adapted Wick's theorem.
The center. Directly the A daggers and the A, but directly have the E, like the generator.
I don't know this, no. So I don't know this. Okay. Okay. Okay, but I thought for spin adapted orbitals, this is much more complicated to perform. So you have to pay the price somewhere. I see, yeah. But I think a more interesting extension of Wick's theorem is that you don't always have to go to the pure vacuum, right? So in this case, you have daggers and non-daggers to the left, and you can imagine if you have a general n-electron state, these strings become pretty lengthy. And then you get many of these brackets to count. You can actually extend Wick's theorem to the Fermi vacuum, which is given by any single Slater determinant. And then, well, certain annihilation operators become hole creations. So this is the particle hole formalism. But this is more of a goodie that if you think this is useful for yourself, you can start working from there. So useful extension is to the Fermi vacuum. Yeah, so you don't always have to go to the full vacuum. Okay. So this is all that I wanted to say about, yeah.
Is taking one reference and then creating false particles.
That's correct. Yeah. Yes. Yes.
Why did you introduce the matrix notation first place? We need to use it and doesn't there.
Well, in the matrix notation, it's very easy to see that these rules are fulfilled.
Yeah.
I mean,
why we use that?
I mean this, you can't just, okay, so you want to prove this, right? Well, so the thing is you want to prove this somehow, right? So you want to know that this result holds true. I've presented it as the ground truth, but if you want to really establish that this one is correct, you have to compare somehow with this expression. And the only thing that you know about this expression is that if you plug in these matrices, they follow the Carr algebra. And then you have certain rules that apply. And although I swapped the indices, but you get the same result. Yeah.
This tensor product space.
Mm-hmm.
I was wondering, why did you have to introduce this tensor product space? And it looks like you're writing these big operators are product of matrices.
Mm-hmm.
Why would you need this representation?
Well, I thought this was useful to show that you have canonical anti-commutation results. Yeah.
But this can be done as well from the definition of the operator that you gave. It can be done.
I guess so, yeah. But I mean, many things can be done, right? But this is very instructive, I thought, but maybe not. It's like,
You explored it computationally.
Huh?
Yeah. You explored
Yeah.
it computationally.
yeah. Maybe it was not as pedagogical as I was hoping, but I think, yeah. Okay, so this was all that I wanted to say about second quantization, and this will allow me then in the next lecture to talk about couple cluster theory and why creation or excitation matrices form a commutative algebra and how we can use this to show equivalence to full CI and etc. I just needed this as a building block. Right.